2, 1. Okay, so here's the momentum test or exam or quiz that I want to be able to go through basically at the end of this momentum chapter for grade 12 physics. So I'm going to do what I normally do is in the description, you're going to be able to find the PDF to this entire document so that you can try the test on your own, so each question, and then you can come back and watch the video solutions if you would like to, or kind of skip over to whichever questions that you would want. I might kind of separate the questions as well, so we'll see, depending on how I'm going to be editing this particular video. But I'm going to start at least with the first 2 questions. There's 5 questions on this particular test that I would love to give students on an exam or a test related towards momentum, so that they're kind of well prepared for university-based stream or any college-based stream physics later on, where they're going to be doing momentum. Okay, so let's get started. So here is question number 1. So the first question has nothing to do with regards to actually calculations. Now, just beforehand, I do want to highlight that I'm going to be rounding final answers in future questions to 2 significant figures, but for this one, it's not going to be necessarily needed. So I like this question a lot because it kind of brings back and reinforces to students the difference between elastic and inelastic. So for each type of the collisions, so you see here on the table, it says elastic, inelastic, and perfectly inelastic. So that happens in the table. I'm looking right here. And what we want to be able to do is we want to be able to answer all of these different questions, which are here on the left-hand side. And then you can do any justifications, okay, for your answers if you have them. So let's take a look and see. So first off, is momentum conserved in elastic, inelastic, or perfectly inelastic? And by the way, inelastic and perfectly inelastic, the difference will be that perfectly inelastic means that in the collision, the 2 objects actually get stuck together. And in an inelastic, it could happen, but I'm going to just assume here that the inelastic means that they're not stuck together. All right. So momentum is always conserved. So here, yes, yes, and yes to all of these. So momentum always holds. And that's one of the key items that you learn in this particular chapter. Kinetic energy is not always conserved. And in fact, it is only conserved under elastic, which, to be honest with you, it's not really realistic, but in the form of studying this in grade 12 or even in first years, you typically do have these elastic collisions where you kind of simplify the process. So really the energy is just conserved. Everything kinetic coming in is all the kinetic coming out. Now, kinetic energy is not conserved under inelastic or perfectly inelastic. And any calculation that you do, and normally, if you do get asked questions to justify, just look at the kinetic energy, and then you're going to be able to tell very quickly if the collision was elastic or not. All right, so that is one key component, which is the kinetic energy. The third question, do objects stick together after the collision? No, this does not happen in elastic, and this does not happen in inelastic. Now, again, I'm making that assumption here on inelastic because I have here perfectly inelastic, and that is the only time that they do get stuck together. And obviously, if you have these and you're asking now the question follow-up, objects separate after the collision, yes, okay, so this definitely does happen in elastic. And then in terms of separation, okay, in terms of inelastic, okay, so this would separate normally, and then this would not separate normally. Although inelastic, of course, doesn't always have to separate. It can partially separate. Now, do the same results, so that last item, do the same results hold for 2 dimensions? In fact, does it hold for 3 dimensions, okay, if you wanted to be able to extend it? And the answer is yes, it holds for everything. All that you have up above holds for the 2D case and then for the 3D case. The only difference in 2 dimensions or even 3 dimensions, although you don't normally study 3 dimensions in high school, but in 2 dimensions is that you have to start breaking things down into components, into its X and Y components. But all of the other stuff in terms of momentum and all the other items would actually hold. So that is question number 1. So not a lot to do here, but a super nice question from teachers or profs to give to their students, just as a reminder, hey, okay, what's the difference between elastic and inelastic? So that's question number 1. Here's question number 2. So in this question, we will have calculations, and I will round final answers to 2 significant figures. You can round it to whatever it is that you please. I'll just make it simple. So we have a hockey puck of mass 0.18 kilograms, and it is struck by a stick. Okay, so here's our mass, and then it asks us 3 questions. If a force of 24 newtons acts on the puck for 0.05 seconds, find the impulse delivered to the puck. So please remember, impulse is nothing else. So normally we designate it in this way. I'll drop the vector symbol maybe kind of momentarily in here, although this is really just a one-dimensional. This is just a change in momentum. So the change in momentum that I have is that, and the way that it can be defined, because of the fact that you have the force which is given to us and then the time, then this would be the net force. And yes, you can have this in terms of a vector and then times the change in the time. So this isn't very hard for us to do because we have 24 newtons multiplied by 0.05 seconds, and we can calculate exactly what that will be. So, it can pop up. So 24 multiplied by 0.05, although I guess you can do that in your head as well. Just move the decimal over, and that would be your result. All right, so this is your impulse, which is newtons, okay, seconds. All right, so we're just sticking up with those units. So that's part A. Okay, so this is what we have over here. So we don't really need mass for, at least for part number A, because of the fact that we had F net, which was given to us. Now for part B, assume now that the puck was initially at rest. What is the puck's final velocity as a result of this impulse? Well, in this case, if we want to know what the final velocity is, then what we're going to be doing is I'm going to be stealing actually this right here. I'm going to duplicate it and bring it down, okay, ever so slightly. So this was for part number A. This is going to be for part number B. And if it is the change in momentum, so that means that this would be your mass of the object, and this is final minus the mass, okay, and this would be initial. All right, so this is your final momentum minus your initial momentum, which is just nothing else but the change in momentum. So in here, this whole entire thing is going to be 0 because they are telling us that we are initially at rest. And then what is the final velocity? Well, I do have all of the information. So notice 1.2, that's coming from here up above. And then I have 0.18. That's in kilograms, so that's the mass of the object, which just leaves me, okay, with the actual speed. So I can calculate what that speed will be. And so for this one, it's 1.2, which is on the calculator, divided by 0.18. And there you have it. And so I'm going to round this to 2 significant figures. As I said, this would have been meters per second. All right, that is our final speed that we would have overall. Now, although it is asking us for velocity, we don't really have any directions within here that are given. So I'm not going to give necessarily a direction provided. So this really is just what the final speed is, because we're not aware what the directions are, at least for this particular case. So that is it. So that's part A, and then part B. So this would have been given you full marks. Part C, in a separate event, a puck is moving, so now they do give us the actual movement of speed and direction. So we have a movement and it is hit by a stick so that its velocity, notice, becomes 3.5 meters per second north. So how does this one look like? So it is, I'm going to kind of zoom in here so that I have all of the information. So this is what's happening. So we're moving east at 4.5 meters per second. It is hit and then it starts to go, I guess, north. So I'm going to just kind of draw it like this. This is 3.5 meters per second. That's north. Now find the change in momentum, right? In terms of so this would be your impulse vector overall. So in terms of finding the change, this is a different scenario. So I know that that is the change in momentum, which is in this case, which would be your momentum final minus your momentum initial. So this is what you would have. You can certainly now substitute the entire thing, okay, so overall, so that you have it. And as you're going within here, so I have this information, I have the mass, So I really have all the different pieces. Now I'm going to write these out. So by the way, in vector form. So here the 4.5 in terms of its vector form, although we know that it's east, so it's easy to break down into its x and its y component. So that is the initial, and it has 4.5 and 0, so there's no y value, right? So there's nothing, no angles in here because we're going east. And then for the other one, because it is moving north, there is no x, there is only a y component, and this one would be your initial, this one would be your final. So now if you substitute this back in, so it would be your mass, and then you can substitute your velocities, Vf minus Vi. You can work them with regards to the vectors. Okay, so what you will have overall is mass is 0.18, and then you have now, so your final velocity, which is, so notice the x components, which is 0 minus 4.5 because of that subtraction. So this is going to be minus 4.5. That's the change. And then your v final, which is 3.5 minus 0, which is just going to be 3.5. So this is what we will have, and then the according units that we need. Now, if you want to find out exactly what this is in terms of its geometric representation, because this would be in x and y components, then we can do that. All right, so there you have it. So I did round everything. So notice here is the change in momentum that we have, or the impulse vector. And then once you take it, then you can use your trigonometry. So you can use Pythagorean theorem to obtain the magnitude, which is going to be 1. So I actually calculated it here. So this is unrounded here. And then you can find your angle that you have by using just 10. And so I found this angle right here, or it's 142 if it's with respect to the positive 0 axis. So there you have it. All right, so that's another question. This was question number 2. It's a fun question relating impulse and then changes in momentum. Here's question number 3. So this one might be a little bit more work, so let's take a look and see what it has. So it has 2 carts. They are moving toward each other on a frictionless horizontal track. Cart A has a mass of 1 kilogram and then is moving at 2 meters per second to the right. And then cart B has a mass of 1.5 kilograms and it is moving to the left. Assume there's an ideal spring bumper and the collision is perfectly elastic. Assume the spring constant is 1,200 newtons per meter. At the moment of maximum compression, the 2 carts momentarily move together with the same velocity and energy is stored in the compressed spring. Assume the collision is, okay, so they mentioned that a couple of times. All right, so let's take a look. Let's draw this out. So what is exactly happening in here? So you have one mass, all right, so here's cart number 1. Okay, so this is moving to the right. This is 1 kilogram in mass, and it's 2 meters per second. Then you have another cart, okay, right here. And this one is 1.5 kilograms. This one is moving to the left, and it is moving at 1 meter per second. So those are all of these pieces of information. So we have all of this taken care of. We have a spring constant, so K, 1200 Newton per meter. So that's that information. We know that it's perfectly inelastic. They mentioned that a couple of times. Okay, so let's now take a look and try to see what they want us to calculate. So for part A, calculate the total kinetic energy of the system before and after the collision. Is kinetic energy conserved? Well, yes, kinetic energy is conserved, and this goes back actually to the first test question that we had, because they're telling us this is perfectly elastic, or meaning just it's elastic in total. So that's one of the key properties of elastic collisions, that kinetic energy is conserved. So all we have to now do is we have to just calculate what the kinetic energy is before, and there's no need to calculate afterwards because it's going to be exactly the same thing. Okay, so in that case, kinetic energy before is going to be equal to, so 1/2 m1, v1 squared plus 1/2 m2 V2 squared. And I have all of these pieces of information. So I'm going to substitute them in and I'm going to get an answer for us. Okay, so let's do that. There you have it. Okay, so that's the first piece, not a lot of energy in here. So they're not moving very quickly. They don't have a lot of mass. So there you have that. Now for part B, find the velocity of the two carts at the moment of maximum compression. So when they are momentarily moving together. So this is a great question because it forces you back to understanding momentum and then how to obtain this information. So we're not going to get this from kinetic energy, but we can certainly get it from the conservation of momentum. So now recall that for conservation of momentum, okay, our formula was this. All right, so magic. Okay, so now let's substitute all of these pieces of information in here. So mass 1, so this is going to be 1 times 2 plus, now be careful here with regards to the signs because these velocities do have a direction. This is going to be 1.5. Now this is to the left, so this is going to be minus 1. So that's the speed here. So I'm putting it minus 1 and the other one 2. And it is equal to now maximum compression, which means that both M1 plus M2 are going to be stuck together and they're going to be moving at the same speed. Okay, so this is what we will have. So now that means if you're going to be adding these two together, that's going to be 2.5 kilograms. So that is just the sum of both of these combined. All right, so that's what we will have. And now I just have to solve for that final, and I'm going to get, is it going to be moving to the right or to the left? So let's take a look. So that's our answer. All right, so it is moving to the right, and that's primarily because of the fact that this one was actually moving much faster. All right, because this one was moving only at 1 meter per second. So that kind of overcame that negative. So there you have it. So that would have been meters per second, and you can put it to the right, although it's positive already. So that's for part B. Now for part C, find your result from part B to determine the amount of energy stored as elastic potential energy in the spring at maximum compression. Okay, so if you want to find out what the maximum compression is, then we have to go back to the total mechanical energy. So and here's the formula for that. So that's our formula. And what we want to be able to find is this. All right. And, you can certainly take a look at the video if you want to, have a little bit more information on that. I can put up a link up above there to that total mechanical energy if needed. Okay, so let's do this. Okay, so this is your total kinetic energy kind of before. This is going to be your total kinetic energy not afterwards, right? So this is actually during that compression, so they're not separated out. So we kind of have to be careful in here. So let's try to calculate all of this, and then this is your elastic energy. So that's how much would be stored in the spring, all right? Okay, so let's do these. So the one on the left-hand side, so that's all of these. We've just done this. So I'm going to, copy and put it back into here. So that's how much we've had initially. Now, on the right-hand side, so this is where we're going to have to be careful because of the fact that we know what the speeds were, okay, so that they were moving at. And notice I can kind of simplify this. So I can have the 1/2 within here, my mass. So the mass of the first one, that was 1 kilogram. The speed, which is 0.2, that's going to be squared plus 1/2. The other one was 1.5 kilograms, I believe. Yep. And then the speed of this one is 0.2 squared plus that elastic energy, which is what we're looking for. So I'm going to compute this, then I'm going to bring it over on the other side, subtract it on that other side, and then I'll have my elastic energy. So I'm going to do that calculation right now. All right, so there you have it. Okay, so it looks like a lot of energy gets stored back in because they don't have quite a bit of energy in here in terms of kinetic energy because they're moving so slowly. So there's a lot of elastic energy that gets now stored back in here. And now for part D, it says find the maximum compression of the spring Well, once you have this, then this isn't very difficult to find because that elastic energy is just kx squared. Now, of course, we have all of this information. So 2.7, 1/2. This is coming from right here. Okay, 1,200. And then you have your x squared, which is the compression. So now I'm going to substitute this in, take the square root of both sides, and I'll find out what x is. And that would be our answer. So it's about 0.067 meters or just 6.7 centimeters. So that would have been the compression in that particular spring. So that's question number 3 for us. Okay, so that one is done. Here's question number 4. So this one says, we have 2 friends on a high-speed roller skates and they collide in an intersection, but one of them is packing 25 kilograms more mass than the other. Assume the lighter friend is at 75 kilograms. All right, so we have 2 masses, so M1 and M2, and now they give us that the lighter one zooms in at a velocity of 15 meters per second. Notice they give us a direction. The heavier one, so this is the heavier one, so this is not twice the mass, but 25 kilograms more. So I'm going to just kind of remove that in. It looks like it's a typo. Okay, charges in at 12 meters per second, and then after the collision, the lighter skater is seen rolling off at 13 meters per second, and again, they give us the direction. So we have quite a bit of pieces of information in here, but because we are dealing with these directions, we're going to have to break this down into its components. Okay, now it says find the velocity, both magnitude and direction, of the heavier skater just after the collision. Okay, so how am I going to be breaking this down? So first of all, let's try to draw all of these different things in here. So now we have a lighter skater. Okay, so I'm going to draw this lighter skater in here. Okay, 15 meters per second, and notice north, so it's 30 degrees from north to the east side. So that's going to be like this. Okay, so please remember. All right, so here this is with regards to north. So you're going you're going to be starting on the north side, and then you're going 30 degrees in this, which means east. That's what this one is, and that lighter one is 75 kilograms. Okay, so now I'm going to break this down into its components because I'm going to need it anyways, right? So this is 15 meters per second. So let's break it all down. So I need its x component, and then I also need its y component right there. Now, if that's 30, that means this is 60 because the right angle would be 90 in total. So this component is going to be 15, okay, and then cos of 60. And this component right here is going to be 15 sine of 60. All right, so those are my x and my y components. I'm going to just leave them like that for the moment because I don't want to be dealing with the decimal places with regards to that. So that's the lighter. I'm going to shift this over. Let's maybe change color in here. And here's the heavier one. So that's going to be the heavier one, and it's 12 meters. So now you're going to be starting from south, and it's 45 east. Okay, so this is going to be looking like this. All right. And again, so what this means is you're starting south. So it's going to be like that. And then this angle right here is 45. Well, so that means, with regards to this is also going to be 45. So that's going to be useful because we're going to be breaking that into its components. So that is 12 meters per second. And again, so I'm going to need this component, the y component, and this component right here, which is the x component. So now for the x component, that's going to be 12 times cos of 45. And then for the y component, I'm going to shift these out, okay, over here. So that y component is going to be 12, and then it's going to be sine of 45, but it is going to be negative because notice it's downwards. All right, so it's downwards. So that's what we have to do. This is where your trigonometry and how well you remember it, okay, will help you. So those are my initial ones. And, you know, this one is 100 kilograms because it's 25 kilograms more. So I have now all of these components. Now, my last component, it says that the lighter skater, okay, so that this lighter skater right there is seen. So afterwards, it's moving at 13 meters per second and east-north. Now, how that happens, of course, it's a different story, but okay, so that lighter skater, so 75 kilograms, and you're starting from east and you're going north. So here you go, that's east, but it's 20 degrees. So this is going to be at 20 degrees, okay, going north, and this is 13 meters per second. So again, I'm going to have two components. I'm going to have one component, and I'm going to have another component right here. So those are going to be my two components that I need to calculate. So this is going to be 13 cos of 20 degrees, and this one is going to be 13 sine of 20 degrees. Both of them are going to be positive. And I have no idea what that final is, which is exactly what I want to be able to find. All right, so now I have all of these. And what I need is the following formula. Voila. All right, so here's the formula. So back into that. So that's the two-dimensional, if you want to watch that video. So let's try to now see which information we have. We have our lighter skater, which I guess I'm going to call M1. We know its initial speed. Okay, so we have both of these. We have the heavier skater, so we have both of these. And then we know that the lighter skater, okay, has this final velocity. So really the only things that we're missing are these two pieces, which is what we want to be able to find. So I'm going to have to now take all of this information, plug it back into this formula. So it's going to give me two equations, two unknowns, and then solve. All right, so I'm going to do that in fast forward fashion so that we can kind of see, and then I'm going to solve it right away for us. All right, so I'm going to be looking and solving for this. Okay, let's get to it. Okay, so I'm going to just pause here just so that you can see how what I did was I just set these things up right there, and notice now my goal will be to solve for the x and then the y component. So I have to just kind of do an algebra and do some computations to find out what those values were. All right, so I'll come back momentarily. All right, so before I compute the magnitude and then the direction itself, so this is what the x and y components would look like. So there's a positive component in the x and then a negative component in the y. I'm going to use now the Pythagorean theorem to find the magnitude, and then I'm going to use 10 to try to find what the angle is. Okay, so let's do that. That will be the last item here. So there you have it. All right, so that's the full computation, depending how you want to write your angles or directions. So it's 5.4, and then it's 337 with respect to the 0. Okay, so if you're going all the way around, or it's just, 23 degrees, as you can see there. Okay, so that would be the second last question. So that's this particular question number 4, and that's part A. Now for part B, it says, now determine the total kinetic energy before and after the collision, and then conclude whether the collision was elastic or inelastic. Okay, so in order to calculate the kinetic energy, so this is going to be a little bit annoying. However, it's a great example because of the fact that now for this, when you're calculating the kinetic energy, sometimes people wonder, how am I going to calculate it because I have various components? Well, what you're going to be dealing with is you need the magnitude, right? So you need the actual speed. So before, you know that this is going to be 1/2 mass of the first one, okay? The velocity of the first one initially squared plus 1/2 mass of the second one, velocity of the second one initially squared. And what is that velocity? That velocity is going to be the magnitudes. So within here, so that's going to be this. That's the 15. And in this case, that's going to be the 12. Okay, so those are the two. So if you're going to be substituting this whole back into here, so the first one was 75. And that's the lighter one, and that was moving at 15 squared, plus the other one was 100 kilograms, and that was 12. 12 squared. So that is before. So I'm going to compute that, and then afterwards, so now after, you do the same thing. So we're going to be calculating this. So I'm going to duplicate it in here, change the color to blue for us. Okay, so that we have. And within here, now, sorry, I have to remove the initial because this is the final. So a little f. So now this is 1/2, again, 75 multiplied by, and this one was moving at 13 squared plus 1/2 times 100, and this one was what we just found, which is 5.4 squared. Okay, and now I have to compute these and see, are they going to be equal or not? If they're equal, then it's elastic. If they're not equal, then it's inelastic. So let's take a look. I'm going to just compute this out and then give us our numbers. Okay, so there you have it. So notice that they're not equal. So it's inelastic within here. I didn't round this to two significant figures. You certainly can. So that would be 16,000 and I guess about 7,800. So there's quite a bit of loss of energy in here. So this would be inelastic. But that's all that you would have to do in terms of those calculations. So this is a really nice example just to remind yourself, hey, I'm just going to be using the magnitudes for velocities if I want to be able to compute kinetic energy. So that's it for that question number 4. Here's the last one. All right, so question number 5. Okay, so that's the last one on this exam. So here is the question. Now, it is being kind of stolen, or at least here I'm referencing. Okay, so from this particular textbook, you can find it. It's not the exact same question, but it's close and it has the same concept, so it's definitely worth referencing here. So it says the smaller and larger objects are initially at rest. So you have, here's the smaller and then the larger object. So they're kind of like held in place there. Now the larger object is hung at an angle of 45. So here's your 45 degrees. All right, that's this angle right there. So that means this angle is also 45. And now, based on this, and it's let go. So I guess it's let go and basically smacks into this one. Now, it tells us the following. Okay, part A. Determine the speed of the two balls after the collision. Assume an elastic collision. Okay, so this is really great. So now, what are we going to try to do here? Because we don't have any speeds. So this is now going to start to combine all the information from physics that you know about kind of in energy and conservations of energy, etc. And you know, this is elastic. So the first thing that we're going to have to do is this. So now I'm going to draw a triangle in here, like so. Okay, and there we have it. So that's that triangle. Now, why am I drawing this triangle? Because, okay, so this is going to be at a certain distance, okay, away from here. Now we're going to assume that those masses are kind of in point form, which means, you know, the 2 meters, it's kind of 2 meters all the way to the middle in here, and then it's 2 meters all the way to the middle over here. Okay, so that's what you would have over there. And now what I want to be able to do is the following. Okay, so this is what I'm going to do. If this is initially at rest, but then when it's let go, then it has a certain amount of potential energy, right? Gravitational potential energy. Now, how much gravitational potential energy does it have relative to this point? Well, I would need to know what this height is right here. If I know what this height is, then I know that the gravitational potential energy
is the mass of the object times gravity times the height itself. Now here's the mass of the object. G is 9.8. Now that h I will be able to find. How? Because if I know that this total distance here is 2 meters, right? Well, that's the length, and then as it swung back down, I know where this is located initially. So I can find out what this height is or what this distance is right there. So how will I know that? Well, this is 2 meters. So if I want to know what this distance is, then that distance is going to be the 2 meters. And then, of course, now it won't matter in this case because it's 45 degrees, but it's going to be cos of 45 degrees. And I will know exactly what that distance is. So that gives me this distance. And then that height, so that height, let's call this distance d. So that height is now going to be 2 meters minus that distance. And therefore, I will be able to find out exactly how much gravitational potential energy I have. So now my assumption will be that all that gravitational potential energy is going to swing over, and where does it go? It goes to kinetic energy. So when this ball finally reaches and hits this other ball or this object, all this kinetic energy, okay, is coming from the gravitational potential energy over here. And if I know the kinetic energy transfers from here, then I can find out what, again, because this would be mass v squared of the kinetic energy of that object. So I will be able to find out what the speed is at that collision. And if I know that speed at the collision, that initial smaller ball is not moving. So its initial speed is 0. And then the bigger ball has a certain speed. So I will now have the 2 speeds, and I will also have 2 masses. So if I have the speeds and the masses, I can find out what the final now speeds are based on the fact that this is an elastic collision. All right. So let me first calculate all of this information. So let's calculate this d. All right. So that's going to be the first piece. And then I'm going to substitute that d into this h. And then we're going to find out how much gravitational potential energy we're starting with that will go into the kinetic energy. All right, so let's do that. So that's my h. All right, so I haven't rounded anything here, so you can keep several decimal places. I have it already on the calculator. And then I'm going to multiply it by 9.8 and then multiply it by the mass, which is 2.5. And that will give me what the total energy here is. All right, joules. So I kept there, I have 4 significant figures. You can keep more if you like. I'll keep this on the calculator as well. Now, all of that goes into the kinetic energy. So all of this gravitational potential energy that I have, the GP, is going to be transferred in, and this is 2.5, and therefore I can find out what that speed is of that big ball. All right, so I have all of this information. So 14, 3, 5, etc. 1/2 times 2.5 times v squared. So I can solve for v. So I'm going to do that right now. So there you go. So we now know, I'm going to call this 2. I'm going to call this 1. So now I have the speed at impact. The second one, so this is v2i, and then this v1i is 0. All right, and now where do I go from here? Because I now found what the speeds are initially. Now, because they tell us that this is elastic, then now I can go back. Let's see if you remember. Now, if you don't remember, you will have to use both the momentum equation and also the kinetic energy equations before and after. Because you know that elastic, they're equal. And then you have to substitute and solve everything. Now, if you are using formulas or if you remember, then you can use those special cases for elastic collisions. I'll put up a link up above there if you want to see that video, because I'm going to just bring in the formulas here just so that I don't have to manipulate everything again. So here it is. This is what the final speeds are. based in these collisions that we have on the assumptions that it's elastic. Now, also we know that one of them is equal to 0. So now in this case, it's V1 is equal to 0, but that, doesn't matter. So I can certainly change these around. Let me, change these so that it goes exactly with this formula. So it says V the 2, so I'll swap these. Okay, I'm going to remove this within here. So I'm going to call this one 2, and then I'm going to call this one 1. So that means this is 1. All right, within here, and then this is 2, and then it will align, okay, over here so that I can substitute all of these in here. All right, so now I can use these formulas to substitute it in. Again, where are they coming from? They're coming from the fact that conservation of momentum and conservation of kinetic energy are preserved, and then you can manipulate the formula. So I did that in the video if you want to take a look at this and where these formulas are. So I'm going to substitute the numbers and then basically just obtain what the answer is. Okay, so let's do that. Bam. All right, so there you go. So that's the beauty of having these equations right there. So we have, the first one kind of slows down. I guess it hits the other one. The other one is smaller also, so it'll pick up and transfer all that energy. So it's 4.2. Okay, so that one really blasts off there, and then the bigger one kind of slows down for us. So that's for part A. So it's quite a lot of work, but it's a great, great question that captures a lot of different items within here. For part B, it says calculate the maximum height after the collision. So this is interesting. Okay, so what is the maximum height that we would have? And then it says state all your assumptions. Okay, so in terms of the maximum height, okay, so for this is really neat because of the fact that the maximum height that it's going to reach is the amount of kinetic energy that it initially has. So for instance, the first one, okay, so I'm going to, we'll assume that it just, kind of keeps going all the way through. So the first one I'll do up above there, and then the second one I'll do right below here. So we need to know how much kinetic energy that they have initially, after that collision. So that would have been 1/2. This is for the first object. So this one was 2.5 kilograms. Now we know its speed, 0. Now I'm going to kind of use the rounded answer here, squared. That's the kinetic energy. All that kinetic energy, right, is going, because it's going to be going up, it's going to then transfer into gravitational potential energy. And if it's going to be transferring to that gravitational potential energy, then we can find its height. So now here is the other one. So this will be 1/2 multiplied by 1.5 times 4.2 squared. So let's get these numbers. Here they are. So those are the kinetic energies that we have from both of those items, those objects. And now, so for instance, so the 0.9, so that kinetic energy is going to transfer into gravitational potential energy, all of it, because eventually it will stop going upwards. So this is going to be 0.9, and then this is mass times gravity times that height, the new height of H1, how far it will reach. So this is not very difficult to now do. This is going to be 2.5 times 9.8. That's the first height. And then here's the second height that you would have. And that's going to go into the gravitational potential energy of that second object. So you have 13.23. And again, this is going to be mass. So that's of the mass first one. This is mass of the second one times gravity times H2, which in other words means that H2 is 13.23 divided by 2.5 times 9.8. All right, and now we can compute these, and then we'll find out what those final answers are. And there you have it. And by the way, I just noticed, because I think I put 2.5 in there, so I just changed that. This is supposed to have a mass of 1.5. But those are our answers, and that's the process that you would have to do it. Now, fingers crossed, okay, I did all the calculations correctly. You know, maybe somebody will catch something, hopefully not, and that everything, the process was correct. I just hope that I didn't screw up on some of the calculations. And that is it, right? So that's the full test. Amazing test in here. So all of these questions, if you were able to solve these, you know, props to you. You would have been much better prepared than I was when I was finishing high school. All right. Okay. So thanks for watching kind of the last test that I had, you know, years in the making between math and physics. I finished all of it finally, you know, hundreds and hundreds of videos. I hope that it has helped, you know, a few people along the way. All right. So thanks for watching, and a new journey begins. Okay. Bye, everybody.